Welcome back. As you can see, our next chapter is going to be about fluids, and it is a relatively short chapter. Let's get started. First, we're going to start out with the definition for a fluid. It can be a liquid or a gas, and I mention this because sometimes most people think that fluids are only liquids, but they can also be a gas as well. So a liquid or a gas, and it's going to have no definite shape. Next, we're going to look at the first of three main principles in this chapter. It will be Archimedes Principle. So the actual principle states, an immersed object is buoyed up by a force equal to the weight of the displaced fluid. Now on the next screen, I'm going to show you a picture and talk a little bit more about what each of these things mean. So when we see that term buoyed up, you want to think about something that's trying to rise up or float in our fluid. So imagine that we have a big giant swimming pool, and I have a beach ball right here. So I don't know if you've ever tried to push a beach ball underwater, but it's really, really hard to keep it beneath the surface. Well, the reason for that is for Archimedes' principle. We have what we call the buoyant force, and it's going to be pointed upward. In this case, if you think about a beach ball and look at the size of that beach ball, well, for our example, I'm trying to push it underwater. So we're going to take that same size beach ball. Imagine if it were filled with water, how heavy that would be and what the weight is. Well, Archimedes' principle tells us that this weight is the same size or magnitude as the buoyant force. So if something has a larger volume, it's displacing a lot of water. And the amount of water that gets displaced would be if we were to take that object and fill that empty space with our fluid. So in this case, since the beach ball has a large volume, it's displacing a lot of water. Think about how much that water that gets moved out of the way would weigh, and the size of that weight is the same strength of that buoyant force that's trying to make the beach ball float back upward to the surface. Next, we're going to talk about pressure. The equation for pressure is a capital P, and I put you a little note, don't get it confused with power. They're not going to be in the same chapter, so that shouldn't be a problem, but I did want to point that out. Pressure is going to be force divided by area. And I made brackets over here for our units. I hope you remember that forces are measured in newtons. And for our area, we want that to be in meters squared. Now this unit has a nickname. It's called a Pascal. If you've ever done any kind of computer programming, that Pascal language is named after the same person. And it's abbreviated PA. So you can tell the difference between the unit and the variable because the unit's going to be PA and pressure is just a P. So I have an example problem for you. We're going to work this out together. We have a car with a mass of 1,400 kilograms, and the area given is already in meters squared. It's 0.135, and that's how much total area is in contact with the road. And we want to know how much pressure the car exerts. Well, we're given a mass in kilograms, so just like you've seen for several chapters now, we want to change that force, and in this case it's going to be a weight, so we're going to multiply mass times gravity. So take a moment and go ahead and figure that out. You should get about 13,720 newtons for our force. The area is already given to us. It says that there's a total of 0.135 meters squared of tire in contact with the road, so it's already taken into account all the tires put together, and we are looking for the pressure. All we have to do now is plug in. So take a moment and try that and come back and see if you got the right answer. You probably noticed that this is a really large number, so I'm going to write out the number and show it to you in correct scientific notation. You should get approximately 1 times 10 to the 5th pascals. When we're talking about pressure, these numbers are probably going to be fairly large, so it might be a good idea to practice using scientific notation. One of the things we'll also discuss is atmospheric pressure. These are 2 numbers that you will need to memorize. Typical atmospheric pressure at sea level is about 101.3 kilopascals. Remember that those are pretty large, so we're going to use kilo to kind of help us with that big number. And you probably don't have a grasp of what a pascal is, but you may have heard of PSIs, especially if you check the air pressure in the tires of a car. Well, PSI stands for pounds per square inch, and the equivalent of atmospheric pressure is about 14.7 pounds per square inch. And one of the things that we'll do in class is I'm going to pass around something that's about 15 pounds, and I want you to get a feel for that and imagine that much weight on each square inch of your body. That's the pressure we live in normally. So I made a few extra notes for you. When we do this in class and you get to feel that big bowling ball on each square inch of your body, imagine that air is a gas, so it is a fluid, and we're displacing a lot of air. We're miles and miles deep into the atmospheric pool. So there is a lot of pressure on top of our bodies. We have that much pressure pushing on every square inch of us all the time. But the flip side is you need that pressure to live. If you take away the air pressure, then you're taking away the air. And this idea of atmospheric pressure, one application of it is for baking. I don't know if you've ever looked on the back of a cake box or cake mix or brownies or something like that, and they give you different directions depending on the altitude that you live in. That's because the pressure is different and it affects how the food will turn out when you bake it. So just a little side knowledge for you. I have another fun fact. In deep sea diving, or if you've ever known anybody or gone scuba diving, you may have heard about the bends. Well, when the Brooklyn Bridge was being built, they didn't really know that you should come up slowly and change your pressure at a really, really slow rate. Otherwise, if you change your pressure too quickly, you get tiny bubbles of nitrogen formed in your bloodstream. And this is called nitrogen narcosis, or the bends. Well, across the Mississippi River on the St. Louis Bridge being built, they actually knew about coming up slowly, so those workers didn't get sick when they were building the bridge. So remember, if you're ever going to go diving, you want to make sure that the pressure that's on your body changes very, very slowly, otherwise you could get sick. And I also mentioned one more demonstration down here, a bed of nails. If you show up to class next time, you will get a chance to lay on an actual bed of nails and see what that's like. But in the meantime, I have a video clip for you to watch. So go back to Google Classroom and watch the video clip provided if you would like a preview of what we're going to do in class. See you next time.
And what's happening?
Okay, we're talking about pressure. So normally when you think of pressure, you think of like weather or something like that, but pressure can be defined a different way. And pressure is when two things come in contact with each other. So here, hang on to the balloon, and a balloon loves a nail. So we can define pressure this way. So kind of watch this. Just see how the tip is right there. All the pressure's at that point right there. And then we get a pop, right? And that's fun. Did you like that?
No.
No, okay. That is not fun. So that's why I'm not using a nail at all. My great friends at the Arizona Science Center loaned me this. Look, it's a little bed that's here, and there's 4,538 holes. And in those holes are this. Look, there's 4,538 nails. So in theory, this should be really awesome, okay? If you can take the pressure and distribute it over the entire table like this, it should be fine. And here, for example, watch. Take an apple and just kind of drop it on the nails, and you'll see that it bounces kind of right off. But that's okay. Your flesh is thicker than this, all right? So it is not a problem. That was silly right there. This is pretty. So what I was thinking was, if you're up for it, I got you this nice little pillow. And then I was just kind of thinking, I'll help you if you just kind of want to lay down on this, and then I'll show you the next part. It's fine. It's clean. Do you want to? Here we go. 4,538 nails. Your body. Isn't that cool? Are you okay?
Yes.
I can't make it go down, but the up part was awesome, all right? I think we're going to be just fine.
And you can feel how sharp they are, like, on my hands.
Sorry. But it's distributed across your entire body, so if you just lay on one nail, you would ruin the weekend, but you lay on 1,000 and you're fine.
Like, if I went to sit up right now, it would be
No,
bad.
you don't want to sit up, all right? So
Yeah.
watch this. It kind of comes back down again, and you are perfectly fine. You can take a tremendous